right, enough with the introductory material that we've been discussing so far. So in this video, we're going to look at the formal basis for finite differences. We've motivated it intuitively from the definition of the derivative, which I'll remind you of in the next slide. We just did it in the previous video, but I'll remind you again. And then we'll look at how Taylor series can be used to formally derive these. So they are called finite difference approximations. We sort of discussed why that was the case in the last video. But let's go back to the definition of the derivative. We had this way back in section 234 as well as in the previous section. So du dx at a given point, x sub i, which we'll denote simply by the du dx with a subscript I here. And that by definition is the limit as delta x goes to 0 of u at a point just to the right of the point of interest minus u at the point of interest divided by the distance between them. So again, this is rise over run. So it's the distance change in u divided by the distance between them. And this is exact, it's an exact expression as long as delta x goes all the way to 0. So in the finite difference context then, we're going to not take it all the way to 0 in order to get an approximation. So we have the same rise over run here, but no longer taking a limit. So delta x will be small, but not all the way to 0. And we'll use a similar shorthand here that we used here, we'll use it down here. So u of x sub I will be denoted as u sub I, and u sub xi plus delta x will be denoted by ui plus 1. So we'll often look at our x like this. So we'll have xi plus 1 with a delta x between them. So that's the way we'll write it in shorthand like this. Okay, so that's a finite difference. We actually call that a forward difference, because the point of interest is right here, x sub I, and we're looking forward to the point xi plus 1 in order to approximate the difference, so we call that a forward difference. So if you look at that graphically, it would look something like this. So here we have u as a function of x, and let's say u of x looks like this. This is u of x. So let's say we have a point right here. So that's the point xi where we would like the derivative. So the derivative I'll put in red here. So the derivative, as we know, is the slope through that point. So it's the tangent through that point, something like that. Now the forward difference says go a delta x to the right, so a delta x to the right, and that's point x sub I plus 1. So the forward difference actually, let's pick another color. Let's use blue. So forward difference actually would look like this, because it goes through those 2 points. So this is forward. So again, it's the point itself and the point to the right. And you look at the difference in u, so that's the rise, over the difference distance in x over the run. So that's the forward difference. Now you can see I've blown this way up so we can actually see what's going on. Normally the delta x would be very, very small. So if I look at that and I say, well, that's not a very good approximation, this is not a good approximation to this. And just looking at this graphically, it's not hard to see a better approach. So a better approach would be, let's choose another point to the left. So this would be x sub I minus 1. So that's a delta x to the left. And if we did let's do it like this. So that was supposed to be a straight line. That's what's called a central difference. So now, so that's a central difference. So now it's the point to the right minus the point to the left divided by the distance between them, which is now 2 delta x's, which is exactly what we have up here. So this is called a central difference. It's ui plus 1 minus ui minus 1, so that's this point, minus this point, divided by 2 delta x, the distance between them. So it's still rise over run, but now to get an approximation for the derivative here, you can see this, the slope of that is much closer to the slope of the tangent that we're looking for as compared to the forward difference. Now that's just motivated graphically and intuitively, and of course you can think of all kinds of different function shapes where that would be even better or worse and so on. So this is very heuristic, very qualitative and intuitive based. But the real question is, how can we derive these using a more formal approach? So rather than just motivating it from the definition of the derivative and motivating an improvement just purely from graphical considerations, how can we get these more formally? And then the second question is, how can we quantify how good or bad these finite difference approximations are? So I think that the central difference is better than the forward difference. Can I quantify that? Can I show formally that it really is indeed better or not? And indeed it is better, and we can show how much better. So that brings us to Taylor series. So Taylor series is something that you saw way back probably in Calculus 1, and then have not used since then, I would guess, other than maybe problem set 1 for this class, where we played the Taylor series, we plotted Taylor series. So I'm going to pull out the Taylor series again. It's very straightforward, very simple, and that's the basis then for this formal approach to getting finite difference approximations. What the Taylor series tells us is the local behavior, so near a point, in the vicinity of some point. So let's say we have a function and we know the value of the function at x sub I, and we'd like an expression or an approximation for the value at x. So to do that, the Taylor series tells us we're going to evaluate everything at this point. So all the function and derivative evaluations are at x sub I, but all for the objective of approximating, or it's actually equal if you include all the terms, getting an expression for the function value u at x. So we have u at x, which is here, is equal to u at xi, which is the value of u at this point, plus all these terms. So each term has an x minus xi, which is this distance here, x minus xi, times, the first term is the first derivative, so du dx, and notice the subscript I here means it's approximated at this point, evaluated, not approximated, evaluated at that point. So the first derivative at that point. Then the next term is the square of the distance, x minus xi, over 2 factorial times the second derivative evaluated here, and then the third, and then the fourth. So the general nth term is x minus xi to the power n over n factorial times the nth derivative evaluated at x sub I. Now if you continue that all the way out, keep all infinity of the terms, then that's an equivalent expression for u of x at this point right here. So again, it's telling us how we can get u of x at a point near another point where we know the value of u and the derivatives of u. And that's my insightful statement down here. You probably remember I got all excited about this way back at the beginning of the semester, but I'll say it again because it really is amazing. So everything's being evaluated at this one point, and what the Taylor series tells us is if I keep all these terms, what that's telling me is all I need to know is the value of u at this point, the first derivative, second derivative, third derivative, fourth derivative, all the derivatives at one point, and that tells me everything I need to know about how this function behaves for all x if it's an equal sign, I don't have to say anything about this distance. What we're going to do is we're actually going to truncate this. We're going to get rid of some of these higher order terms, and so we truncate it, and by doing so it becomes an approximation, in which case this distance has to be small enough to warrant that approximation. But if I don't make that approximation, if I keep all the terms, if I don't truncate it, then this is an exact expression. It's very, very powerful, very interesting. All right, so this is the general equation. 7.4 is the general expression for a Taylor series. And what we're going to do is apply that at various points. So first, I'm going to set x is equal to xi plus 1. So remember, xi back here, xi is a specified point, and then x is a point I can move around on the x-axis. So now I'm going to fix x to be at x of I plus 1, so the next point to the right in my grid. And so now xi plus 1 minus xi, which remember we see in every one of these terms, that is going to be xi plus 1 minus xi, and we'll denote that by delta x. So I'm going to substitute in delta x for each of those xi plus 1 minus xi's. You see those here. And then now, where I had u of x, it's now going to be u of xi plus 1. So now we're getting an approximation for u at the point to the right in terms of the point itself, ui. And so here's that Taylor series. Same as before, substituting ui plus 1 for u of x and delta x, which is this distance, for the xi plus 1 minus xi. So why did we do that? What can we do with it? Well, I can now solve, for example, for du dx. So this would give me an approximation in principle for the first derivative of u with respect to x evaluated at x of I. So that's the slope of u at x of I. So if I solve for this, I bring this term over to the left. I'm going to flip everything around. So now I have ui plus 1 minus ui divided by delta x. I've highlighted this portion in blue because that's actually the portion we're going to keep. Everything else is going to be truncated, but we have all the rest of the terms. So the next term is delta x squared over 2 divided through by delta x, and that becomes delta x over 2. Don't forget the minus sign here because we've moved this over to the other side of the equation. And that carries through for all of the terms. The term that we really care about is this first one. That's called the truncation error. It's the first term that's truncated. We'll talk more about that in a little bit. But for now, that gives us an approximation for the first derivative of u evaluated at x of I. Let's do it again. That was kind of fun. So let's do it again. So let's set x is equal to xi minus 1. So now it's the point to the left. We did the point to the right. Now let's do the point to the left. So now xi minus 1 minus xi is going to be minus delta x because we're going in the negative direction. So when I substitute in for my general Taylor series, again I'll have the ui minus 1 that we're getting an approximation for in terms of ui, which is the same as before. But now all of these xi minus 1 minus xi's are going to be minus delta x. So we have minus delta x plus delta x squared because that's even, so the minus minus gives you plus. Then the odd term gives you a minus, so it's plus, minus, on forever and ever. Once again, I can do the same thing. So let's solve for this first derivative. It's the same as this one up here. So I'll get an alternative expression for the first derivative of u with respect to x. And here it is. So it's ui minus 1 minus ui divided by minus delta x. So that flips this around. So I have ui minus 1 over delta x. And once again, the next term would be delta x over 2 d squared u dx squared evaluated at x of I. And you'll notice now it's a plus sign instead of a minus sign. And on and on and on for all the rest of the terms. But we're going to again focus on this as our approximation, and then we'll look at this first term that's been truncated and see what that tells us about our approximation. Now there's one more I can do with this. So what if we were to subtract the Taylor series for xi minus 1, the one that we just did, that was equation 7.7, and subtract that from the Taylor series for xi plus 1, the first one, which is equation 7.4. If I subtract those equations, I get this expression, and now, again, I can solve for du dx at I. So let's do that. So now I'm going to have ui plus 1 minus ui minus 1 divided by 2 delta x, so that's what you see right here, and that's du dx. The next term, again, I divided by 2 delta x, so that becomes minus delta x squared. It was delta x cubed, now it's delta x squared over 6. It was 3 times 2. And then again, for the rest of the terms. So summarizing this, what we have are 3 different approximations for precisely the same thing. All of these are approximations for the first derivative, du dx at x is x sub I, but they're different. One is called a forward difference. This is exactly the same as the one that we obtained intuitively from the definition of the derivative. This is what we call a backward difference, because unlike the forward difference, it's the point and the point to the right. Now it's the point and the point to the left, so we're looking backwards. And then a central difference is ui plus 1 minus ui minus 1. So we're looking at the point in the middle. We take the difference of the u's at the surrounding points to the right and left, divide by the distance between them, 2 delta x, and that's the central difference. And if you look back, that's exactly what we got when we just, again, did this intuitively in the graphical context. So what does this tell us? First of all, we do have a formal basis for where these derivatives come from, these finite difference approximations come from, by truncating these Taylor series. But not only that, we have a measure of the error. We call this the truncation error because it comes from truncating the rest of the Taylor series. So to get these terms, which I'll describe the notation in a minute, you simply look at the first term that's been truncated. The first term that's been truncated here is of order delta x. Now the 1/2 and this derivative, those are just numbers. The delta x is small. And you'll notice that each of the subsequent terms has a higher power of delta x. So if delta x is small, then delta x squared is even smaller, delta x cubed is even smaller. So the largest term that is the first one being truncated is this one. And it's of order delta x. Likewise, this one is of order delta x. This is the forward difference, backward difference, and central difference, you'll notice, is order delta x squared. Once again, the minus 1/6 and the third derivative, those are just numbers, order 1 numbers. So the size of this term is given by the delta x squared. So you see that here, order delta x, order delta x, order delta x squared. And that's how we say this. So this big O, some people call it big O notation, but the way we actually say it is order of. So the first one, forward difference, is order of delta x. Backward difference, order of delta x. Central difference, order of delta x squared. So as you'll see in the next slide, we call this first order accurate, and this is second order accurate, the order of the delta x multiplier. So again, the two things we get are formal derivation of these finite difference approximations, and we get the truncation error, so we can show formally that indeed the central difference is fundamentally better than the forward and backward difference. Again, because delta x is small, so delta x squared is even smaller, which means it has a smaller truncation error than these second order versus first order. Some comments. So I mentioned that's the truncation error for small delta x. It's the first term that we truncate that determines that truncation error. I said this, first order accurate versus second order accurate. And as I just mentioned, it is indeed true that the central difference approximation is fundamentally better, provably better, not just because I happen to choose the correct function and put the points at just the right spot, but it's fundamentally mathematically better than the forward or backward difference. Now, one thing you should keep in mind in the context of our numerical solution procedure, this is step 2, this is the discretization step that we're talking about. And so this truncation error arises because of our choice of the algorithm. So by saying I'm going to use finite difference approximations of a particular type, that determines the truncation error. Same thing as if I were to use a finite element method, that would determine the truncation error. The round-off error, which we discussed earlier in the semester, comes from a different source. That comes from the fact that we're doing calculations, additions, subtractions, multiplications, and divisions on numbers, but on a computer, of numbers on a computer. So the truncation error is always there. It's a fundamental error based on the algorithm, based on step 2, based on how we've discretized the governing differential equation. So that is an inherent error of the method, of the algorithm. I could have a perfect computer that does exact arithmetic. I still have the truncation error. So that perfect computer will get around the round-off error, so it would have no round-off error, but I still have truncation error. So it's important to understand all the different sources of the errors, and there's convergence errors, truncation errors, round-off errors, and so forth, modeling errors, which we discussed last time, and understand, again, what the source is so we can understand how to mitigate those errors. Now we want other derivatives. So if you think back to the spring mass system that we had in the last video, we had first derivatives, which we just dealt with, but we also had a second derivative, d squared u dx squared. So how can we get a second derivative? Or how can we get other derivatives, derivative approximations? So let's look at first the second order accurate forward difference approximation to the first derivative. So what we just did was a first order accurate forward difference approximation to the first derivative. Now we want to find a second order accurate. As you might imagine, to get a higher accuracy in a finite difference approximation, you need to include more points. So far we've looked at the point itself, the point to the right, and the point to the left. Let's look at 2 points to the right. So that would be xi plus 2. So if we write down the Taylor series, that's now u evaluated at xi plus 2 is equal to ui. Now the xi plus 1, well, the x minus xi is now 2 delta x. So you see 2 delta x here, 2 delta x here, 2 delta x here, because we're going 2 delta x's away from our reference point. Now, if you look at this, I want a approximation of first derivative, but I want it to be second order accurate. So remember what happened last time. If you remember the procedure, I had this divided by, this minus this divided by what's now 2 delta x. But the truncation error term, because I divide through by delta x, this became a delta x. That's what gave rise, delta x to the 1, that's what gave rise to our truncation error. So I want to get rid of this term, because if I can get rid of this term, then the first term that's kept is this one, which is now a delta x squared. It starts as delta x cubed, but then I divide through by delta x, and it becomes delta x squared. So if I can get rid of this term, then I can solve for my first derivative, and I'll have a delta x squared order accuracy, second order accuracy. So if I stare at these Taylor series approximations long enough, I can convince myself that if I take 4 times equation 7.5, remember 7.5 was the, so let's draw this. So now I have xi plus 1, and xi plus 2, and each of these are delta x away. So now I want to, if I take 4 times 7.5, so remember 7.5 was the Taylor series at this point. Well, we just got up here, 711, Oh, that makes me hungry for one of those nasty meat things rolling continuously for hours. Oh, oof. Okay, sorry about that. So we have the Taylor series 7.5 for this point. 711 is the Taylor series for that point. Oh, I can't get it out of my mind now. It's horrible. And so if I take 4 times that one minus 711, then I get this. So what happens now? So now I just take this over with these two. So I'm going to have 4ui plus 1 minus ui plus 2, and then bring this over minus 3ui divided by 2 delta x's, and that gives me my approximation for du dx. And again, the first truncated term is now going to be this one, but divided by 2 delta x. So it gets rid of one of these delta x's and it cancels the 2 to give me delta x squared over 3. Okay, so that's the truncation error. So it's second order accurate. And then the approximation looks like this. And you'll notice it involves the point of interest, the next point to the right, and the next point to the right of that. So ui plus 1, and ui plus 2. But now we know how much of each. This is basically a weighted average. Minus 3 of these, plus 4 of those, minus 1 of those, gives us the finite difference approximation that we're looking for. All right, now let's get it. Again, we needed a second order accurate central difference approximation of the second derivative. So we have a second order accurate central difference for the first derivative, du dx. So to be compatible with that, we would like a second order accurate central difference for the second derivative. So how can I get that? Well, if I look at the first two Taylor series I wrote down, 7.5 and 7.7, which are for ui plus 1 and ui minus 1, and if I look at those to determine how can I eliminate the du dx term, well, I just add them. In fact, let's go back and just see that. So here's 7.5, and here's 7.7. And you'll notice that the first derivative here term is plus delta x. This one is minus delta x. So if I just add these two together, this term will cancel with this one. Why do I want to do that? Because now the first derivative, not the first derivative, but the now the derivative that appears first in my Taylor series is actually a second order derivative. So I can solve for that because I've gotten rid of the first derivatives. That was close. So when I add those together, I get this expression right here. Now I can solve for d squared u dx squared. And we get this in blue. And once again, we get the first term that gets truncated, which is order delta x squared. So this, which is ui plus 1 minus 2ui plus ui minus 1 over delta x squared, which we're going to see over and over and over again, is order delta x squared accurate. So it's a second order accurate central difference approximation. It involves the point to the right, the point to the left, for the second derivative. So we have that for the first derivative, that for the second derivative. We're good to go. Okay, a couple more comments. So when you compare these first order and second order accurate forward difference approximations, you'll notice that, as we said, to get higher accuracy, you need to include more points. So for only 2 points with the forward difference, I could only get first order accurate. To get second order accurate, I needed 3 points. So this can get very complicated very quickly, because you've got to figure out how much of one Taylor series, how much of the other gives me what I want. As you can see, the 4 times this minus that. How do you figure that all out? So it can get quite complicated very quickly. So whether we're looking for higher order derivatives or higher order approximations, this can get nasty. So there is an alternative method. I'm not going to, it's in the notes, it's grayed out, you're not responsible for it, and I'm not going to go over it. But there is another method, and basically it starts with determining the finite difference stencil, which is basically those points that we want to include in the finite difference approximation. And once you've decided on those points, so say it's xi plus 1, and xi plus 2, then you can determine what's the highest order finite difference approximation that's possible given those 3 points. So what's the optimal approximation combination of those points that gives us the highest order approximation? Or you can say it another way, the smallest truncation error. So here's a couple slides on that if you're interested, 3 slides on that. Again, I'm not going to go over it, you're not responsible for it, but as you get higher order and it involves more terms, turns out this method is easier than our method. All right, so that's it for the formal basis of finite differences. Next, we're going to look at boundary value problems in Chapter 8, followed by initial value problems in Chapter 9. All right, see you in the next video.